All right, so one of the things that we're going to start to do, and it's going to be very helpful if you do it as well, when you're looking at a circuit, draw like little plus and minus signs around the circuit. So what we tend to think is we have a current, it's going to come up out of the positive terminal of the battery, and it's going to move around the circuit, okay? So let's just call, how many currents are in or flowing through this circuit right now? How many paths does a current have to follow? Yeah, just one.
Two?
Nope. How many? There's only one path. So one way to know if you have more than one path. So I'm just going to do this on this circuit, like, and then I'm going to erase it. But if you start off at one terminal of a battery and you go up and around the circuit, and you don't have to lift your pen up before you get back to the starting place, then it's just a series circuit. It has one path for the current to follow. There are two batteries in the circuit, but together they only create one current. And to go with the convention that your book uses, I'm going to just start using a capital I. That way it's easier for you guys to follow your book. Okay, so I'm going to start using a capital I for current. So if we have our electric current, it comes up out of the positive terminal of the battery. I'm going to put a little positive sign here and a little negative sign on this resistor, okay? And I'm going to make a little note of what I'm doing because we're going to come up with some rules for this. So like as an example, one of the things that I've been trying to emphasize is that current goes from a higher electric potential to a lower potential electric potential. So this is high electric potential. This is low electric potential. So you go from high energy to low energy. So your electric current should flow from high electric potential energy to low potential energy. Now, the other thing that and this is going to be really important for this lesson, whenever you have a current flow across a resistor, you're going to have a voltage drop along that resistor. So delta V, your voltage drop will be negative across a resistor. When you go from high potential energy, electric potential energy, to low potential energy. Okay, so that's an important part of this note right here. Okay. All right, so what I just want to do is continue to follow along, like just adding all of the negative signs and the positive signs. Okay. And this is just going to help us, not so much for this circuit, but for the next circuit that we do. All right, so what I want to do is, what is the current? So let's find the current. And let's just call it, we'll just say find I to make it nice and easy. So we're going to find the electric current. Okay, so there's one electric current, but there's 4 different voltage changes. Okay, so we're going to call this some different color. So what we're going to do is we're going to add up all of the voltage changes along this circuit. And what we'll see is they should all add up to be 0. Okay, this is called Kirchhoff's voltage rule. Kirchhoff was like a Russian physicist about 150 years ago. Kirchhoff's voltage rule. And we've actually been using this rule, okay? This is one way to write it, but I'm going to show you how to use it. So the first thing that we're going to do is we're going to start here. So we'll start here, and we're going to go around the circuit and then add up or subtract the different voltage changes. So going out of this 12-volt battery, we'll see that we have a voltage increase of 12 volts, okay? And then as the electric current flows through this 50 ohm resistor, we're going to have a voltage drop, okay? So I'm going to like subtract So we don't know what the voltage drop is, but we know Ohm's law says that the voltage equals the resistance times the current, okay? V equals IR. So I can subtract this. So subtract 50 ohms. And I'm going to ignore the units just to make it easy to write so that we don't have to keep on writing all of these units. So it's going to be 50 ohms times the current. All right, so that's our voltage drop from Ohm's law. And then I'm going to get to, and notice also for this one, the current is flowing from positive to negative. Flowing from positive to negative means a voltage drop. And then I'm going to have the current, still have one current. It's going to flow from negative to positive. So this one should be a voltage increase. We're gaining voltage, so plus 8 volts, because we're going from the lower voltage to the higher voltage. That's what the battery does. The battery increases the energy of the circuit. So it's going to take a low energy electron or low energy charge and increase its energy by 8 volts. And then we're going to get to, then the current gets to this next circuit, or sorry, this next resistor. And notice we have the positive here and the negative here. Okay, so we're going from higher electric potential to lower electric potential. So it's going to be a voltage drop. And we're going to use Ohm's law again. We're going to say 30 ohms, but I'm going to just leave the 30 out to make it easier to keep writing. Times the current. Well, we don't know what the current is. We'll call that I. That's what we're going to find. And Kirchhoff's voltage rule or voltage law says that if you add up all of the voltage changes in a closed circuit, they all add up to be 0. Okay. So now what I'm going to do is I'm going to combine like terms. Okay. So if you notice here, I have 12 volts here and 8 volts here. So I'm going to add those two voltages together. So 12 volts plus 8 volts should be 20 volts. And then I have these other two like terms. So minus 50I, 50 times the current, minus 30 times I. So that should be minus 80 times the whatever the current is. And those two numbers should add up to be 0. Okay. So now I have 20 volts minus 80 ohms times I. So I can now put this term over to the other side by adding it to both sides. What you do to one side of an equation, you do to the other. And so you should now have 20 volts. Let's do this a different color. You should have 20 volts equals 80 I. And now to find I, you need to divide both sides by 80. And when you do that, you should get I equals 20 divided by 80 is like what, 1/4? So would that be 0.2?
It's 2. That's 1/2, I think.
Uh,
No, never mind. Never mind. I made a mistake.
Thank you for, I make a lot of math mistakes because I don't use calculators. So if I do make a mistake, please let me know. What units do we want for this? What are the units of current?
Ampere.
Yeah, very good. So we can just write capital A. We can write capital A for amperes, or we could say, or, amps. Both of those would work. Right. All right, so that's what the current is that's flowing through this circuit. A couple of things I just want to point out because this circuit's different than the circuits that we have looked at before. This one has 2 batteries in it, okay? So this one has 2 batteries in it, not just one. So that's why we're using this Kirchhoff's voltage rule to solve for this one. Now, what I'm going to do is I'm going to give you a slightly different problem, and I'm going to then have you guys try to solve it, okay? So here's the problem that I would like you guys to try to solve. All right, so I'm going to draw a different circuit. And I have, it's going to look similar, but it's going to be a little bit different. All right, now, so go ahead and draw this circuit. And the first thing that I'd like you to try to do, all I want you to do at first, predict which way you think the current will flow in the circuit. So there's only one path for the current to follow, all right? This would be considered a series circuit. What I'd like you to do is just to try to predict in what direction will the electric current flow. All right, so I'm gonna go ahead and I'm gonna just start to draw on here. So the electric current should flow in this direction. So this will be my guess, all right? And the reason I'm guessing it's gonna flow in this direction, so this is a 50-volt battery. And if you look over here, there are two other batteries that are connected. And there's a rule that we'll talk about later. But if you have two batteries and they're connected like this, where it's, so like this would be the positive terminal. Hang on one second. If this is the positive terminal and the negative terminal, the positive terminal and the negative terminal, when you have two batteries like this, in this case, let's say 10 and 20 volts, when they're connected, like negative to positive, positive to negative, you just add them up to get the total voltage that they add. But um, all I'm doing that for now is to show you that, all right, well, 50 volts is the bigger voltage than 30 volts. So it should be the 50-volt battery or voltage source that's driving the current, that's causing the electrons in the wire to move in one direction. If you guessed the wrong direction, so if you were to say like, oh, the current should flow in this direction, if you were to say that, that's completely fine. What you'll notice is the only difference between the current that, in this case, the current that I find here, let's call it this one, I1, and maybe like I2, the only difference would be the sign. Like one of the currents would be positive, one of the currents would be negative. We don't really care about the sign of the currents yet, okay? So if you got a negative current, so if the current is negative, you chose the wrong direction, realize the current flows in the opposite direction. Okay. So I know that this current is not going to flow in that direction. Okay. All right. So now what you should always do, because the circuits are going to start to get more complicated, I want you to go through and put the positive and the negative signs along the different circuit elements. So what I mean by that is, well, I have a positive here, a minus here. Those are my terminals of the battery. And I know, or at least I'm guessing, that the current is going to flow through the circuit like this. So this first resistor should look like that. Would you go ahead and put the positive and negative signs on the remaining three circuit elements? Okay. So what I'd like to now do is I want to do the same thing. I want to find what the what the current actually is. I want to find a number. So I'm gonna do that same. Oops, sorry. So I'm going to apply Kirchhoff's voltage law again. You don't have to write this first step. This just lets me know that we're going to apply the voltage rules. So I'm going to start with the 50 volts. So we do 50 volts, and then we're going to have a voltage drop across that first resistor. So we're going to do minus 30, and I'm going to leave the units out. We still have one current, and I'm going to call it I. So it's going to be minus 30 I. Okay. Now, if you look, we now have this current that's coming down here, and it's going to go from the positive to the negative side of the battery. Okay, so when that happens, that's actually going to reduce the energy of the electron, okay, of the current. So we're going to subtract for this first one minus 20 volts, all right? So like for the electric current to flow through this battery, it's going to actually decrease the energy of the current of each charge, okay? So when you go from positive to negative, right? That's why I'm having you guys draw these signs as you go around the terminal, all right? You have a voltage drop, and again, you're going to have what's happening? And you're going to have another voltage drop as you go across this 10 volt battery. It's going to be minus 10 volts, okay? And then you have one more voltage drop as that current goes through that 70 ohm resistor. So it's going to be minus 70 times whatever the current is, which is what we're looking for, I. And all those things are going to add up to be 0. Right? All right, so now what you do, you're going to combine the like terms. So I have 50 volts minus 20 volts minus 10 volts. So that should be 20 volts when you add all those numbers up. And then you're going to do minus 30I minus 70I. So that should be minus 100. That's like 100 ohms, right? So just keep in mind we're not writing the units. And that's going to equal times I. That's your voltage drop. And then those are going to add up to be 0. And so when you do this out, you should get I equals 20 volts divided by 100 ohms. And so what is that, 1/5? What does that work out to be, 0.125? Tell me if I'm right, I'm just kind of guessing.
No, 0.2.
0.2, thank you, okay. So 0.2 amperes, or amps. All right, any questions on this one? Because like what we're doing is we're doing two relatively simple problems so that we can do a more difficult problem, okay? So does anyone need this up still? So does anyone still need that? Okay, so I'm gonna get rid of that and make some more room. All right, so now this is where everyone starts hating electric circuits. Okay, let me just erase this. All right, so let's take a look at this other circuit. So I'm going to just go ahead and draw this one. So all right, and once you draw it, could you go ahead and go around the circuit and label, for example, I know that this is going to be my positive terminal, this is my negative terminal. Can you go around the circuit and to try to label what is positive, what is negative? All right, so while you're doing that, I'm just going to go ahead and I'm going to say a few more things. What I want you to look at while you're looking at this circuit, how many paths does an electric current have to follow? Does it have a single path or does it have more than one path? All right, so one of the ways that we can see how many paths a current has is if we just choose one starting point and try to go around the entire loop without taking our pen or pencil up. If I go around here, well, I get to the starting point here, but I still have like another loop here. So like in this case, this is going to have more than one electric current flowing through it. All right. So whenever you have more than one, what we call a branch, you're going to have more than one electric current flowing through it. So first, let me just clean that up, get rid of that. All right. And so this point right here is called a junction. And there's something really, there's something very intuitive about a junction. So if you just redraw that over here, okay. So one of the ways to think about what's happening is you have an electric current that flows up through this circuit, okay. So I'm just going to draw that electric current like this, okay. Some of that current is going to flow down this path. Some of that electric current is going to flow down this path, all right? To know how much current flows down each path, we'd have to apply Ohm's law to figure that out. We'd also have to know what the current is at first, and that's going to be our first goal, is to determine what is the current in each of the, these are called branches, all right? So this branch and this branch. So we're going to try to figure out what the current is in each of these branches. And then we can go ahead and figure out like voltage drop across each resistor or each circuit element. I'm sorry, let me make that a little bigger. All right, so I'm going to call this current that flows out of that 30-volt battery, I'm just going to call this current 1, okay? So if I call this current 1, all right, then I can just say that, well, all right, so when you get to this junction, some of that current is going to flow down here. Let's call that current 2. And then some of that current is going to continue to flow over in this direction, current 3. So one of the ways to think about this, all right, this is called Kirchhoff's junction rule or Kirchhoff's current rule. And it basically just says that, let me put this in English first. The current into a junction, current in equals current out. Okay, so the current that flows into a junction equals the current that flows out of the junction. Or in terms of like an equation, it basically says that the current, in this case I1, what goes into a junction is going to also come out, is equal to I2 plus I3. Okay. Now, for the purposes of this problem, it's easier if we do one additional step right away, and I'll explain why we do it after I kind of show you. So I have this other current here, I3. I don't really like to have too many variables in an equation or in a circuit, so I'm going to just change this up a little bit, and I'm going to write I1 minus I2 equals I3. All right. Does everyone see what I'm doing so far? I'm just taking that up, the current that goes into a circuit equals the current that goes out. And I'm just going to rearrange it to have an equation for current I3. And that's what this term is over here. It's equal to I1 minus I2. All right. This is going to save us a math, actually maybe 2 or 3 math steps later on. So I'm just going to do it right now. Okay. So I'm also going to put on the other diagram that we have here. All right, so this is just to explain Kirchhoff's current rule. So this current down here is going to be sorry, that's not I1, that's I2. Make that a little bigger. So this is going to be current I2, and I could write this as I3, but it makes too many, makes an additional math step. So I'm going to write this as I1 minus I2. Where did I get that? That's what I just found out over here. Okay, so I1 minus I2. So we have 2 loops. We have 2 paths for the current to follow. So I'm going to have to create 2 equations to find the current. The 2 examples that we started class with, they only had 1 path for the current to follow. So there was only 1 equation to write to find the current. Now we have 2 paths, so we're going to have 2 equations to find the current. So we're going to find I1 and I2. All right. From this, we can then find current 3. All right, so what we're going to do is we're going to add up the voltage drops, the voltage changes in each loop. So let's call this loop 1. So this loop here, this is going to be loop 1. And then this loop here is going to be loop 2. Okay. So for loop 1, So I'll call this the voltage changes loop 1. All right, so starting from the 30-volt battery, so our current's going to flow up out of the 30-volt battery, and we're calling this current I1, okay? So our first voltage is going to be 30 volts. This battery is going to supply energy to the circuit, and that's going to cause the current to flow. And then if you look, that current I1 is flowing through that 2 ohm resistor, and it's going from positive to negative. So it's going to be a voltage drop across the resistor. So I'm going to do -2, and I'm not going to include the units. I'm just going to write this as 2. In this case, my current is going to be I1. So I'm going to write it as -2 I subscript 1. And then that current's going to get to the junction right here, and some of that current's going to flow down this way, some of it's going to flow down the other path. But we've already said that the current that's going to flow through this 5 ohm resistor is going to be I2. It's not current I1. It's going to be current I2, all right? It's not going to be the total current. It's only part of the current. So I'm going to also subtract -5 times I2. And those all add up to be 0 because there's no more resistors to go to before the current returns to that battery. All right. I'm going to do one more step. I'm going to just take these terms and I'm going to push them over to the other side by basically adding 2I1 plus 5I2 to both sides. So I should get an equation that says 30 volts equals 2I1 plus 5I2. This is going to be our first equation. Notice this has 2 unknowns in it. Whenever you have an equation with 2 unknowns, you need one more equation to find out what those other unknowns are. All right. So looking up here, all right, and let's erase some of this to make it easier to see. Okay. So now we're going to look at the second loop. So we're going to look at the voltage changes for the second loop. Let's write that down. All right, so now we're going to have this current. It's going to flow. So this is current I1 minus I2. It's going to flow from negative to positive. So this current is flowing in the correct direction. So we're going to add that first voltage. So this should be 10 volts. And then we have that same current. It's going to flow through this resistor. And notice it goes from positive to negative. The reason that we identify what side of the resistor is positive, higher electric potential, and lower minus negative electric potential, so we can easily see what sign, positive or negative, to include on the voltage. So it's going to be minus 3, and what is that? So this current that we're calling it is I1 minus I2. So minus I1 minus I2. Good. I just have to go back up to see. Now, if you look, all right, so some of that current continues on in this direction, and some of it, it's not really going to continue upwards because we have this other current. So remember, this is I2. And if you look, I2 is going from, like, if we follow this assumption, it's going to go from um, positive to negative. So we're going to add, what number is that? That's 5 ohm. Plus 5 times current I2. And those are going to add up to be 0. All right, so the first thing, distribute the negative sign to each of these terms here. So we're going to do a little bit more math out, more simplification. So we do 10. So we do 10 volts minus 3 times I1, 3 times current 1, minus times another minus sign, a negative times a negative is a positive. So plus 3I2, then bring this term down, plus 5I2, and that's going to be 0. Now you got to combine like terms. So let's see, we only have one where we have a 10 volt. In this case, so I have an I2 here and an I2 here. So I'm going to add these two up. So let me just continue with what we have. 3I1 plus 3I2 plus 5I2. That is 8I2. And those are going to add up to be 0. And just like in the last equation up here, I brought these two terms over to the other side. Okay, so that's what I'm going to do down here. So when I do that, I get 10 volts equals 3I1 minus 8I2. Okay, so this is going to be my second equation. All right. And I'm going to just rewrite those equations right over here so that we can work with them. All right, so if I'm writing these down correctly, I should have, so make sure I don't make a mistake writing this down. I think the first equation was 30 volts times 2I1 plus 5I2. And I think the second one we wrote as 10V equals 3I1 minus 8I2. All right. All right, so now I'm going to eliminate one of the terms from here. All right, so I have two unknowns and I have two equations. Like if you guys knew, do you guys know matrices? Like you know how to use a matrix? Some of you do? Okay. All we're going to do is like, we're going to treat this like a matrix. I'm going to find a common term to eliminate. So I'm going to eliminate, I1 to find I2. All right, so I need a common term. So like, all right, if I'm going to eliminate I1, I'm going to multiply the entire bottom equation by 2. And I'm going to multiply the top equation by 3. And I can just choose one of these to be negative. So let's call the bottom one, we'll multiply it by a -2. Okay. Just to help you see what I'm doing, I'm going to take the additional step and I'm going to just rewrite each of these terms. So this, this top one should be 90 volts equals 6 times the current I1 plus 15 times the current I2. And that bottom equation should be minus 20 volts equals minus 6I plus, what is that, 16 I2. All right, does everyone agree with that so far? All right, so now all you do is you add these two equations together. So 90 minus 20 should be 70 volts. 6i minus 6i should just be 0. And then 15i2 plus 16i2 will be 31i2. All right, so then the next step, we're just going to solve for I2. So you just divide both sides by 31. And so you should find that I2 equals 70 volts divided by, remember that's like 31 ohms. What do you guys get when you do that?
2.258.
2.25, let's just round that to 2.26. And that should be amperes. All right, so now we know I2. So now what we can do is we can substitute this back into one of those equations. So to find, say, I1, substitute. So you're going to take this value for I2, choose one of those two equations that we started with. So I'm going to choose like the one with the smaller numbers because it's like easier. So I'm going to just choose this equation. I'm going to just rewrite it over here. So this is 10 volts equals 3I1 minus 8 times I2, which we just found I2 to be 2.26 amps. So I'm going to substitute it there, 2.26 amps. And remember, this is a unit of a resistance. So can someone tell me what 8 times 2.26 is? That's a 2.26. What's 8 times 2.26?
18.4-ish.
So
18.08.
18.08. So can I round that to like 18.1? Is that okay?
Yeah.
And now that those are units of volts. Let me just write that 8 a little bit better. So 18.1. Because sorry, 18.1 volts. Because here this is a unit of an ohm, and this is unit of amperes. So an ampere times an ohm is volts. Okay. All right, so now I'm just going to add this to both sides, 18.1 volts, 18.1 volts. And when you do that, you should get, was that 28.1 volts equals 3I. So if you divide both sides by 3, can someone tell me what I1 works out to be? What is 28.1 divided by 3?
9.36 or
9.36.
37.
All right, we'll say 37. And that will be units of amperes as well. So now we know two of the currents, so that now we can just go ahead and we can find current I3. So way back up here in the very beginning somewhere, we figured out that I1 equals I2 plus I3. That was Kirchhoff's junction rule or Kirchhoff's current rule. So from Kirchhoff's current rule, we know that I1 equals I2 plus I3. And we know that I1 equals 9.37 amperes. We know that I2 equals 2.26 amperes. So can you guys tell me what I3 is. So it should be 9.37 minus 2.6. So is that like
7.11 S.
7.11 you said?
Yep. Yeah.
Oops. All right, so now we know all three currents. We know current I1, we know current I2, and well, current I2 was this, 0.26 amps. So now what we can do is we can use that to figure out the voltage drop across any of the resistors. And let me just do a quick time check here. All right, so we're starting to go into office hours. So like I won't keep you for the entire time. But what I'd like to do, so hang on, let me share a different screen. All right, if we go back into the materials section and we go back into electricity and magnetism, there are those practice test 1 questions. And let me just share that from a different screen. Okay, I don't know why that's not there. All right, so for Thursday, what I would like you guys to do is make sure that, so I think we did problem, so make sure you have for Thursday, not for tomorrow, so for Thursday, okay? Tomorrow, you're gonna have like a 4-question quiz, all right? But tomorrow we'll also be doing these after the quiz, so like make sure you do number 1, number 2, not number 3. All right, number 4, okay. I think we did number 5 in class. Ignore that one for now. We did number 6 in class, I think. Do number 7. And do number 9. So these are not for tomorrow, but for Thursday. Okay, so for Thursday. So tomorrow, what we're going to do tomorrow is we'll come in and you'll have your 4-question quiz, and then we're going to just work a lot of problems. That way we get really good at solving problems. That way we get you guys prepared for all of the assessments that are going to be coming up. Okay. So hang on 1 second so that I can just do attendance. Okay. So I should put this, so hang on, let me just